Okay.
Right. We're going to move on to Justin Schonker. I'm really interested in whether he's actually calling in from Adelaide, Australia today, or maybe someplace a little bit closer. We may be in on his Saturday morning, early in the hours. I'll let him speak to that in just a second. He's been an assistant professor at the University of Tulsa, where he established a diverse research program in organic chemistry and material science. Since 2015, he's been an associate professor at Flinders University in Adelaide, Australia. Justin's research program spans diverse priorities in green chemistry, environmental remediation, and sustainability. These interests have led to a long-term commercial collaboration with Clean Earth Technologies, developing products and processes for remediation and safer and more sustainable mining. So he's going to be speaking today about an oil sorbent that's made from sulfur and cooking oil. You're on, Justin.
Thanks, Ellen. Can I just check first that you can hear and see me clearly?
I can hear and see your face.
All right. All right, fantastic. And I am calling from a very early morning in Adelaide. So thank you very much for having me. I will go ahead and share my slides. Okay. Ellen, can you see the slides and still hear and see me all right?
Yes, all good to go.
Okay, fantastic. So yeah, greetings from South Australia. I run a research lab at Flinders University, and we've recently assigned a portfolio of patents for some of the polymer technology we've developed at the university. And we're working to translate that commercially with a company called Clean Earth Technologies, which operates out of Singapore, Perth, and Adelaide. And the basis for these materials is that we're interested broadly in sustainability, in using very low cost sustainable building blocks to make useful materials, and perhaps even convert waste into materials that can be useful in environmental remediation. We've deployed a number of these polymers in sustainable activities, including eliminating mercury and cyanide from gold mining. We have an e-waste recycling operation that uses these materials to capture gold. That's here in Adelaide. We use these materials in mercury remediation. We can convert these materials to recyclable rubber and composites for sustainable materials for the built environment. In another project, we use these sulfur-based polymers as slow-release fertilizers, and even ventured into the adhesives world. And today, obviously, we'll focus on the applications in oil spill remediation. But I want to emphasize at the outset that a lot of the core polymers that we're using, we deploy them in all of these applications. So like I said, I'm calling from Adelaide, Australia, so it's just 5:30 in the morning now, so an early start for me. Clean Earth Technologies operates out of Singapore, and they have an Australian office in Perth in Western Australia. So we became interested in using sulfur as a building block to make these oil sorbents because there's a lot of sulfur geologically, and we make a lot in oil refining. So we make more than 70 million tons of sulfur per year in the desulfurization process of crude oil. And that's a good thing. So when we burn petrol and diesel, we're not making sulfur dioxide, which ultimately gets converted into acid rain. But we have a surplus of sulfur that's produced globally. So even though we use elemental sulfur for fertilizer, for vulcanized rubber, we still have tens of millions of tons of sulfur that remain in above ground deposits worldwide. And so in our academic lab, we thought it might be useful to try to find new ways to convert this abundant feedstock into something useful. And it's very low cost. We buy it directly from a refinery. We essentially pay for shipping. And if you make a polymer from sulfur, it's quite distinct chemically, physically, mechanically than carbon-based polymers. So the backbone of these materials actually contains sulfur-sulfur bonds rather than your classic carbon-carbon bonds of polyolefins. And that imparts some unique chemistry that allows some versatility in the applications I mentioned in the beginning. So we can use these materials made from sulfur. So these materials contain over 50% sulfur by mass. They have a polysulfide structure. They can react and bind with mercury. So we use this material mercury remediation of soil, water, and air. The same material, because it's hydrophobic, sulfur is hydrophobic, We can use triglycerides of canola oil or used cooking oil to make these materials as well. They're hydrophobic, so they're quite useful to bind oil. The sulfur imparts affinity for metals, so not just mercury, but also precious metals. So these polymers are integrated into mining and e-waste recycling processes as well. And so when we started this, again, at the outset, we wanted to make useful materials from waste or things that are easy to get a hold of. So sulfur is very cheap. Canola oil has this unsaturated triglyceride structure right here. So when we do this direct copolymerization, sulfur reacts with these carbon-carbon double bonds in the triglyceride, and you make this rubber-like material. We can make it porous by putting in a porogen such as sodium chloride. You heat this up, and then you can wash out the salt and you can get a porous polymer. You can also inject air to avoid the washing step and make it even more efficient in a single operation. We can even use used cooking oil. So our lab will go down to the student pub and get some of the used cooking oil. So we have gallons and gallons of this to make some of these materials. So in principle, it can be derived entirely from waste. Obviously, if we want to deploy this in oil spill remediation or any type of environmental remediation, we need to scale this up. So our first go is to run this in 2 kilo batches in our lab, and so you can see that here. This was first carried out by Dr. Louise Asdale, who now is an employee at Clean Earth Technologies. To scale this up even more, we designed a batch reactor so we can process 10 to 20 kilos at a time. So again, we're just using sulfur and waste cooking oil to make this sorbent. And then most recently, we've used this as an information gathering exercise to understand this reaction so we can make even larger quantities. And we now have a reactor where we can process nearly a ton per day. So this is scalable. The building blocks are virtually free. And so that allows us to deploy this in a variety of applications, as I mentioned before. And in terms of oil spill remediation, the hypothesis is not too surprising. This is a hydrophobic material. It's low density, so you can have buoyancy. We see a water contact angle here of around 130. So it doesn't take up water, and it will bind to oil. And as you've seen in many of the talks, some of the features that would be required for a versatile oil sorbent: you want it to be fast, have high capacity in its binding to oil. You want it to be cheap and scalable. In many cases, it's useful to have buoyancy. You don't want it to take up water, and you want to be able to reuse it. And so this is just a particle of the porous polymer made from sulfur and canola oil. And within seconds, it binds to diesel motor oil, crude oil from Nakatunga oil fields in Australia, and West Texas crude oil also. Even the really viscous oils bind to this material rapidly. So obviously, recovery and reuse is important. We can control the material properties of this material so it behaves as a squishy sponge or a powdered particle. But because of this compressibility, it allows you to recover the oil just by simple mechanical extrusion. So you can squeeze this, recover the oil, and then you can reuse that material again and again. Another thing that's useful is that when you cast this sorbent on oil in the powdered form, it aggregates, which can facilitate recovery, or you can deploy it as a filtration media. And like I said here, you can reuse this many times and recover the oil. At the end of its life, we're looking at different options. We can actually carbonize this and then reintroduce that carbonized material into other remediation activities at Clean Earth Technologies, including mercury recovery and gold recovery. So here's just a video about how this works. So Flinders University is very near the coast. So we take the lab down to the beach, get some seawater, head back to the lab. So here's some raw crude oil. So this is West Texas crude oil, just poured directly on the seawater. And we're doing this at room temperature here, but it also works if the water is cold. So if you're thinking about Arctic conditions where the water is minus 10 degrees, it works fine. The polymer in powdered form typically takes up to 5 times its mass. So the capacity, is not the highest performance, but the material is incredibly cheap. It binds on contact, and you can compress and recover it, so you can reuse it many times. So the student who did this experiment here, he left it for a minute just to make sure it bound everything. But as soon as it touches the oil, it aggregates and converts it into a gel. And while we're not necessarily advocating casting this directly on an oil spill, this is mainly just to show how it does aggregate that oil. And then that you can compress that and recover 90% of the oil and reuse that material again and again. So probably more realistically, how this would be deployed is as filtration media and in a continuous process where you have the oil and the water or the contaminated water pumped through the filter, the oil is bound on contact, and then you have a piston compress that media, pump up the oil to recover it, and then you can reuse the filter again and again. Here's just a simple demonstration of having that same crude oil water mixture, and you can pour it through the filter, which is packed with the powdered version of that polymer. So again, we're using only waste materials, so you can consider sulfur a byproduct of oil refining. We're using used cooking oil, and then we're deploying that resulting polymer in an environmental remediation context. So we think that's a neat idea, a neat way of thinking about sustainability and developing sorbents and deploying them in a sustainable and useful way. So you can see here the water passes through because it's a hydrophobic polymer. It doesn't interact with water. That passes through the filter, and the crude oil is retained. So this is just the crude oil that's just bound to the surface of this tube right here. The bulk of the oil is bound to the polymer. And then, like I said, you can have a piston to compress and pump out the oil to recover it. Okay. So I wanted to keep my presentation short, so I'll go ahead and stop there and just provide a short summary. So this material, it's made entirely from waste. In principle, every atom in this sorbent is derived from waste cooking oil and sulfur, which is a byproduct of petroleum refining. The uptake of the oil is fast, so this is scalable, so this is available in ton quantities. We actually were involved in the process chemistry to build that reactor and plant here in Adelaide. It's made from waste, so there is an environmental aspect that's we think is intriguing in the manufacture of the material. This is buoyant. There's interest in Australia in evaluating this as a free sorbent that's cast from aircraft, especially in mangroves where it's very difficult to access. And we're now evaluating, after it aggregates the oil and converts this into the gel, can we actually have that degrade in situ? Because this material is biodegradable, we actually use it as a component of fertilizer. And so can it trap the oil and then have that degrade over time in a way that prevents the oil from harming wildlife or plants? So we're evaluating that currently in mangroves and wetlands that are otherwise difficult to deploy other types of remediation technology. It has a wide temperature range, and this works also in cold environments. The polymer interacts with oil in the same way, even if you're below zero. You can recover the oil, so even if you don't have the massive capacity, because you can have this in an automated process where it binds, you compress and recover the oil, you can reuse that over and over again, for instance, in a filtration media, just like I'd shown in the videos. And you could also deploy this base material in some type of bunding or sock if you wanted to use it in that context. All right, so that's my presentation. I know it's a bit short, but that gives us a little bit of time for questions. I want to thank my research team here and Clean Earth Technologies, who is manufacturing and commercializing this class of materials for a variety of applications in remediation, mining, and oil spill remediation. So thank you very much for your attention.
Oh, thanks, Justin. Thanks, Justin. I think maybe you have a secret urge to get onto building your breakfast for yourself here, but before you do that,
Not really, yeah.
let's see if we have a couple questions for you.
We do have a couple questions. For your separation experiments, did you analyze the hydrocarbon content that remained in the water?
So there is some trace hydrocarbon content in the water, and we have analyzed that by gas chromatography. Our main interest was to make sure that the slick is removed as a first priority, so it's not coating the larger waterfowl and fish, for instance. So there is trace hydrocarbon, as you might imagine, that does remain in the water. So this is not purifying it to the extent where it would be safe to drink, for instance.
And a comment to start from Scott Smith. Thanks, Tom. Please let me know when you'll be visiting and love to get together with you. And a question, do you have wave tank test options available to you in Australia?
We do actually. So the Maritime Safety Authority in Australia is the governing body for deploying all oil spill response technologies. And so we're working with them and some of the contexts that I've talked about before. So field work in mangroves, but also they have large tanks for the more realistic large scale evaluation. And so all of the technologies in Australia have to go through them before they can be used commercially.
I apologize in the comment. I was reading something that wasn't supposed to go to this presentation. Sorry.
Very happy to meet up with them as well.
Sidebar conversations.
All good.
Those would have been happening in a room otherwise. So, I mean, it's good that we can be distracted by sidebar conversations, even on virtual platforms.
It's all great.
It's all good. So Justin, I think if we had awards to give for the person who had to flux the most in meeting our time zone, I mean, we don't have an award to give, but I mean, if we did, it would go to you. Thanks.
Very happy to be here, and thanks everyone else for the presentation. It's a good way to start the day.
Okay, thanks for joining us.